All right, I'm going to go ahead and skip example number 5, but let's look at example number 6 together. It gives us more of an application problem. So we've talked about derivative. We've talked about the interpretation for derivative, that it's really the same thing as an instantaneous rate of change. It's really the same thing as the slope of my tangent line. Let's go ahead and apply it now to an application piece. So it says here in example number 6, the cost in dollars to manufacture X graphing calculators is given by this equation. So X is the number of calculators, and C of X is the cost to manufacture the calculators, right? It says here to find the rate of change of the cost with respect to the number manufactured when 100 calculators are made and then when 1,000 calculators are made. So we want to find the rate and change of the cost depending on how many calculators we manufacture. We want to find the instantaneous rate of change when 100 calculators are sold, the rate of change at exactly that time, and then we want to find the rate of change at exactly when 1,000 calculators are manufactured. So what we're looking for here is an instantaneous rate of change, or the derivative, right? And so we can take this application problem, and anytime it asks us for an instantaneous rate of change, a rate of change at one moment, we can apply that limit idea and find the derivative, or the rate of change. So let's do it here. Let's take this function, let's apply the limit as h approaches 0 of f of, or in this case c of x plus h minus c of x all over h. So wherever I see an x in my equation, I'm going to plug in an x plus h. Then I'm going to subtract the function again, c of x, all over h. So yours should look like this now. I have the negative 0.005 times an x plus h squared plus 20 times an x plus h plus 150 minus my f of x, so the whole entire equation again, making sure that I put parentheses around it so that I remember to distribute that negative through, all over h. We're done with the calculus part. The rest of it is algebra, but this is where we're going to make most of our mistakes, so be careful. I need you to pause the video. I need you to FOIL, distribute, and combine all of your like terms. Hopefully, all of your terms without an h should cancel, right? So pause the video and then come back and see if you have all the same terms I do. All right, after I FOILed, I was left with the x squared plus 2xh plus h squared. I distributed my 20 through, and I distributed my negative 1 through. So I have this. I still have to make sure that I distribute this negative 0.005 through, so I'm going to do that now. And hopefully you have all the same terms that I do. All right, let's reduce. It looks like I have a negative 0.005x squared and a positive, so those cancel. I have a positive 20x and a negative 20x, so those cancel. Ooh, I have a positive 150 and a negative 150. So it looks like all the terms that are left over have h's, so that makes me feel good because that's what's supposed to happen, right? So now that all the terms have h's, I can factor out an h. I would have left over a negative 0.01x minus a 0.005h plus a 20. The h in the numerator, the h in the denominator reduce, and so then I have the limit of this leftover piece. I can smush my 2 points so close together by applying that limit process. Let's plug in a 0, and I end up getting the derivative as negative 0.01x plus 20. I said f prime. This is probably supposed to be c prime, right? Because our function was c, so this is really c prime. So what this is really my instantaneous rate of change at any moment. So I can figure out my cost, my change in the cost at any time of making these calculators. I can figure out the change in cost when x is 1, when x is 3, when x is whatever, right? And so this is the change in the cost. Remember, the question asked us to find the rate of change in the cost when we manufacture 100 calculators, and then again when we manufacture 1,000 calculators. So let's finish the question and do that. Let's figure out what the cost, how the cost is changing when we manufacture exactly 100 calculators. I'm going to take this and plug it into my derivative function. Again, I accidentally was using f's because that's what a bad habit, what we're mostly used to. This should really be c prime of 100. So let's plug in 100 to my derivative. I ended up getting 19. So what would that mean? What would your interpretation for the meaning of this 19 be in context to the problem? And let's look for three things. When is this happening? What is happening? And what is your answer with correct units? The three things. All right, I said when 100 calculators are produced, the cost is increasing by $19 per calculator. It doesn't cost $19, it's increasing by $19 per calculator as soon as I manufacture 100 calculators. So right before I manufactured 100, maybe 99, it was a little bit lower. It was $19 lower. Now it's increasing. When I go to produce the next calculator, it's going to be $19 more per calculator that next time. When 100 calculators are produced, the cost is increasing by $19 per calculator at that exact moment. So let's figure out what the cost change is when we manufacture 1,000 calculators. If you plug in 1,000 to your derivative, you should end up getting 10. So write a sentence interpreting what that answer means with the three things. Okay. Did you say something like, when 10 calculators are produced, the cost is increasing by $10 per calculator? So if I'm this manufacturing company, if I'm owning this business, I want to make sure, and I would rather produce 1,000 calculators because my cost is only increasing by $10 per calculator. Versus if I manufacture only 100, then the cost is costing me $19 per calculator when I manufacture only 100. So my goal is to try to hit the least cost, right? And so it looks like it costs us only $10 per calculator more than it did before. It's increasing by $10 per calculator. Now, we could kind of play with those numbers a little bit and figure out where it's going to cost us the least, and we'll talk about that in another chapter. But for right now, we can find the rate of change in the cost at any moment, the instantaneous rate of change, by finding the derivative. And this works in any context, whether it's manufacturing calculators or in chemistry, whatever it might be. Anytime we're looking for an instantaneous rate of change, we can apply this formula.